My lecture today is called Computer Vision in a Web Browser. I wrote these slides a few days before the war, so of course I forgot everything, but I'll try to tell you something. Next slide, please. Lecture outline. Part 1, an introduction to browsers and JavaScript. Part 2 is CV in front of backend. Then I'll tell about WASM and Emscripten, computer vision and OpenCV with Emscripten, deep learning in browser, and finally other libraries and technologies. Next slide, please. We start with a part 1, a very brief history of web browsers. Initially, HTML was like PDF. It was pure static format. Later, dynamic HTML and HTTP protocol and nothing else. In year 95, JavaScript appeared. A first language running natively in each browser through a JavaScript engine, a kind of virtual machine. Soon after that, CSS appeared. Also Java applets, which were very nice, but unfortunately this technology was deprecated and doesn't exist anymore. And finally, a few years ago, about 5 years ago, WebAssembly appeared, a second native engine to run in a browser, or a third if you count Java applets, and which basically replaced the Java applets technology. And in recent times, there is HTML4. And front end is typically not just HTML, but an entire application written in JavaScript frameworks. It interacts with the backend via REST API, like get, post, put, delete. Originally, while this put, delete, and so on were part of HTTP protocol from the very beginning, they were never used for years, and only recently they have been used as part of REST protocol. HTML4 with its video playback, streaming, camera, etc. supported in all modern browser. And things like Adobe Flash Player are deprecated, and in general, browser plugins are in the process of dying out. Next slide, please. I'll very quickly give a basic terminology of web browsers for those who are not familiar with this platform. Window is a browser window or tab in modern browser. Frame is a sub window. Document is HTML in a window frame. There are other standard objects in JavaScript in browser like navigator, location, and so on. HTML is composed of HTML elements or tags which are open and closed. And there is something called document object model or DOM3. Every HTML element is a JavaScript object and can be accessed by proper hierarchical path or by search functions like get by ID, query select, and so on. Next slide, please. JavaScript is a language that does only exist in browser. It's a modern object-oriented language which has old object syntax a few years ago extended by the new class syntax. All more than JavaScript is used in a strict mode. Use strict. All variables must now be explicitly defined with let or const, or the var is deprecated, but it's still JavaScript has no explicit types like Python. Apart from the absence of explicit types, the syntax is rather similar to Java or C++. Modern JS is not only in browser. Node.js is used for desktop, backend, and also for building JavaScript apps. Various mobile frameworks, usually based on HTML and JS. Electron, desktop, GUI framework, and Qt Quick extensively the uses JavaScript for desktop GUI, and there are many other applications of JS as a language not only in browser. Next, please. Web browser nowadays is a virtual machine which can run JavaScript natively through the JS engine, such as V8 or others. In the 20th century, HTML was like PDF for doc, and browser was like a PDF viewer. Not so anymore. In this century, a browser is a virtual machine which you can compare with Nintendo or PlayStation emulator running on your computer. My experience that browser is a very bad platform. It's really hell, worse than mobile or Raspberry Pi. Thus, I'm a bit skeptical about doing computer vision and other complicated tasks on the front end because browser as a virtual machine is very bad. It cannot run native machine code, except if you as browser plugins with technology mostly dead. It tends to be 10 to 100 times slower than native code, like on your computer, except with exception of built-in browsers stuffs like video codecs and WebGL. Basically, it turns your modern PC or modern iPhone into something really slow, like Raspberry Pi 1 by speed. Also, browser sandboxed and hyper secure. You're extremely limited in what you can do. For example, you cannot access your file system or devices of your computer. Camera is complicated and so on. Browser, the virtual machine, contains basically two engines, JS engine and WASM engine, which they can combine, of course. And other languages like C++ are compiled into WASM. More on that later. Next slide, please. And I continue. Many things like camera require HTTP as you cannot run them HTTP, not even on local host, or you need to special browser settings, and to show it to somebody, you need to buy an HTTPS certificate. Cannot freely access different remote servers. There's something called CORS, very unpleasant limitation. You cannot autoplay videos with sound and tone of other completely artificial limitations, which makes it very unpleasant to develop anything for front end. Mobile browsers has no browser console and no local host server, making it more difficult to debug anything or on phone browsers. Lots of things are built in into modern browser. Then it's reasonably fast and efficient, like email loading images, canvas, video, audio playback, WebGL, streaming, and so on. But you have very little control. You're allowed to do only what they allowed you to do. And and if you're trying to do something different, the custom things is going to be very slow. Basically, my opinion again is web browser is not a platform made for computer vision. Well, it's definitely not made for computer vision. It's made for things like I don't know, or in internet shopping or at most some kind of video connection to other people, not for computer vision. Next slide, please. And as you might know, there is a video tag in HTML4 which can play videos and can also play camera videos, but there are a lot of issues to it. It all looks nice in demos, but if you try to use it in computer vision, I discovered many interesting things. For example, seeking to position in video file didn't work for me on Chrome. And you cannot break video into frames. There are no next frame callback or anything like that, or callback which is called frame after frame, or waiting for next frame or anything like that. So you cannot really process video frame after frame. It's real time only. You cannot wait for the next frame until you process a frame, even if you process a video file. The main thing is that all these video tags are made for playback on screen, not for processing video. Like everything in browser, it's made for some stupid things like, I don't know, video streaming, like Google Meet, but definitely not for processing the video. What are the alternatives? There is a new experimental video API called Web Codecs, but it's very experimental and not yet supported. everywhere. And there is also a thing like FFmpeg JS, Emscripten port of FFmpeg, but it's huge and can be slow because it's not browser native. Basically, there are no good alternatives for working with video in browsers. Although web codecs in a few years could make things a little better. Next slide, please. Very briefly, I can tell that in old times JavaScript was loaded by HTML script tag, had global scope of global variables. Nowadays, there are JavaScript models. They are loaded by import statement, but Node.js has its own system of modules which existed before import statement appeared in browsers. They were loaded by require function, and there are tons of nice stuff in the npm repos of npm, the package manager of Node.js. Unfortunately, it works only in Node.js, not in browser. Can I use npm model in a browser? Not directly. You need something called a bundler. Next slide, please. What is JavaScript bundlers? In old times, web page consisted of HTML, CSS, JS files, and the no builder, like C++ code you build into executable. But JavaScript in old times, it was like Python. You don't have to build anything, just to run. But nowadays, things changed. You need bundlers to compile JavaScript, well, to JavaScript, like building C++ project. Why do you need to compile JS to JS? There are several reasons. And by the way, they typically use Node.js on your computer and npm to configure and build projects. And there are Browserify, Webpack, Parcel, Rollup, many bundles. Why do you need to compile JS to JS? There are several reasons. First, you can with bundles you can use npm modules in browsers. So there are thousands of modules in JS you can download from internet and use in your project. But you can only use it for browsers with bundler. You can also bundle multiple JS files into a single JS files. You can create minimal or obfuscated JS. You can also transpile different languages like TypeScript, Dart, even Kotlin into JavaScript. And you can transpile also JS to all the JS version for all browsers. Maybe not so important nowadays, but used to be popular. You don't need to know much about bundles. I just mentioned that such thing exists, and professional front-end developers always use such thing, always. Next slide, please. And the related thing is JS frameworks. Nobody nowadays writes production code in pure JS if you are a front-end developer. And various front-end JS frameworks provide high-level GUI API, typically based on model view controller paradigm or something similar. Interaction with the backend via REST and other goodies. There are many frameworks like React, Vue, Svelte, Angular, and so on. Typically, they use a bundler to build all stuff together, which is of course nice, but I didn't learn any JS frameworks yet because it makes a much steeper learning curve. You have to learn JS language, and you also have to learn JS frameworks, which looks a bit different from pure JS. But of course, if you are a professional front-end developer, you have to know at least one, probably more of these frameworks. Next slide, please. Now finally we're finished with this JS introduction, and now let's discuss computer vision in the browser. First question is, should we do CV in front or back end? For many people, first reaction should be, why not use back end? Powerful search, AWS, Amazon, Google, Azure, whatever. But I would say that probably not very good idea. For example, we would like process a video on a server. Usually it's not very good idea, although you can use server for database, for user accounts, stuff like that, but not for computer vision. Why? The reason network latency. It could take half a second or even 1 second sometimes in two directions to send information front end to back end. And nowadays, if you have Starlink, some satellite internet is going to be worse. The second in network throughput. Video streaming to server and especially to WASM can be a bit heavy for bad Wi-Fi like I'm having in my place, or for example for cell phone could be expensive. So maybe it's not very good idea. And also, how do you do streaming from browser to server? For web browser, there is technology called WebRTC, which is supposed to be good, but if you can try, but it's only made for peer-to-peer direct video communication. If you're trying to make anything non-standard, it's complete hell. If you're trying to do WebRTC, sending video to server, is complete hell. You need special software called WebRTC gateways. It's very complicated. Or you can use WebSocket, much easier for programmer, but you cannot use highly compressed codecs. Then your video will be JPEG or even raw pixels, which is not very efficient for network usage. While WebRTC uses network efficiently, but it's absolute hell to do on server or if you're trying to do some custom computer vision. Next slide, please. So let's do, I forgot to say it's not very good idea to send video to the server. It's better to do computer vision on the front end. Next topic, you probably all heard about WASM and Emscripten. What it is? WebAssembly or WASM is a binary instruction format for WASM virtual machine in a browser. It's different from native machine language for Intel or ARM, and it's much slower than the native machine code on your computer. Whatever they say in these advertisements, in reality, is going to be 10 times slower or even 100 times slower. Just realize, don't believe the advertisement. And how to create this WASM virtual code? LLVM, sorry, it was supposed to be not CMake, but CLang. Has WASM platform. Is it enough? Not really. You also need standard libraries and all kind of additional stuff to efficiently use C++ from JavaScript. That's where Emscripten comes into play. It has LLVM plus C and C++ standard libraries, complete toolchain, and many additional GUIs for better connection between JavaScript and C++. Idea is build your existing C++ code into WASM, then call it from JS in a browser. Next slide. How do you compile C++ to JS? It's pretty simple. Just as you compile normally C++ into executable, here you use em++ instead of G++, and the output will be hello.js JavaScript file and not a machine executable. Or for CMake, you use the typical CMake build with the prefix emcmake to set up the proper Emscripten toolchain. You may have also heard about ASM.js. What is ASM.js? It's an efficiently optimized subset of JS, and it is an older alternative to WASM. It's deprecated nowadays. You should never use ASM.js without a good reason. Use WASM instead. Next slide, please. But of course, the idea is that you can compile any C++ code into Emscripten is good in theory. In practice, well, things are not that easy. There are many gotchas and pitfalls of Emscripten. From the point of view of C++, the JavaScript plus WASM is executable, not a library. Remember this, never called it library. But in practice, it's used as a library because you can call C++ function from JavaScript and might not contain the main function. But it's not a library and shouldn't be called a library. A library is a different thing. Node.js can execute such builds directly if they have main function. C++, cout, and printf work in browser and print to the browser console. Of course, if you have the console. On mobile browsers, you don't. You can you can access the access to browser variables like DOM and browser GUI from C++ is very limited. Typically, you should access your web page from JS and use C++ only for some algorithm. The exception is WebGL, which can be efficiently called directly from C++. C++ cannot access JavaScript data, including binary arrays, without copying. However, JavaScript can freely access C++ heap. So, so the basic idea that all data to be used by C++ should be copied to C++ heap, which is very small by default. You need compiler flags to make it larger. By default, Emscripten creates old-fashioned JavaScript script. If you want a module, you need additional compile flag. I checked, it works. Emscripten runtime takes time to load, so don't use C++ functions immediately when the web page starts. Only when Emscripten runtime loads, you can call C++ function. And most importantly, it's a browser, so C++ cannot access your PC file system. Next slide, please. Emscripten minimal example is shown here. You need external C so that function can be seen from JavaScript, that it's without C++ name mainly. Emscripten keep alive means that it's exported from this JavaScript and not removed when doing C++ optimization. Here multiply two double numbers, return the result, and also print the result into the screen, standard output, which is browser console. This is a minimal Emscripten example in C++. Next slide, please. You build it as usual with the M++ instead of G++ and load with HTML script tag, your HTML. All Emscripten can be web pages with Emscripten cannot be opened in browser directly. You should run them on localhost web server like Python 3 -m/3 HTTP server. Then open localhost in browser and in GL console type module my_move and multiply the two numbers. See the result, it works. If you are using modules, then global module is replaced by some other objects. I skip technical details. Next slide, please. How do you call C++ from JS? You can call directly, like I showed you my_move, but it works only with primitive types and pointers. It's fast and you have total control. So all things considered, I prefer calling functions directly. This way you are responsible for what you do. Unless you do mistake yourself, you will never get any memory leaks, segmentation faults, or unneeded copying. I recommend this. But for people who want some more high-level interface, there is a function called crop of Emscripten, which give a bit high interface with some support for JavaScript arrays and strings, usually with copying. And there is even more sophisticated binding called imbind, which is similar to nbind of Node.js and pybind 11 of Python, which can wrap on various C++ types and even classes, but use it at your own risk. It's easy to make mistakes like memory leaks when doing such things. I'm not really so learn the details if you want to use it. Next slide, please. More gotchas and pitfalls of Emscripten. As you might have heard, the web browser has problem with multiple threads. While your CPU nowadays typically have 8 or 12 or something logical cores, just a couple of years ago, WASM supported only one thread. Nowadays, there are experimental threads via WebGL. You need special compiler flags. I didn't experiment here, but things are slowly getting better. But originally, it was only one thread in WASM. C++ exceptions by default are disabled, which is not nice if your C++ code there is users exceptions. You can enable them using which slows down the code a bit via JavaScript exception or the very recent and experimental WASM native exception. Next slide, please. I show you very simplified video processing example. You take an, or actually not video, but image processing example. Video is similar. You take an image from image there. Here there is some JavaScript statements which I don't go into detail. You find the various HTML text by their type or ID and find width and height, and you copy image to canvas. From canvas you can get the data as a pixels, RGBA, always RGBA, never RGB, always RGBA, as JavaScript binary array. Next slide, please. Then you should look, C++ cannot access your JavaScript arrays directly. You have to allocate the buffer around the C++ heap using cmalloc function, as you can see here, and copy all your data into that place where C++ can see it. There you call the C++ code with pointer and number of bytes process is some kind of C++ functions which processes the image and the result, which I assume at the same place, although it can be a different heap image, you copy back to the canvas and show. That's the typical pipeline, the simplest possible pipeline of a JavaScript code which uses C++ for image or video processing. Next, please. Now, what if we want OpenCV? OpenCV for image processing, you typically want OpenCV, at least in our company. How do you do it in Emscripten? There is something called OpenCV JS. OpenCV can be built with Emscripten, and it's generally possible, but there are several buts. It uses a custom Python build script, not plain CMake, and the script only worked in the very old version of Emscripten, while the current version is 3 something. What to do? You can either use the ancient version in Emscripten for your project, as I did for the Barges project, by the way, but then you can miss some new features, optimizations of the later Emscripten versions. Or you can use a new version of Emscripten, but then you have to hack the OpenCV build script, which is a lot of trouble. Some people try to do that, I didn't yet. What I can say, shame on you, OpenCV, really shame. Did they abandon OpenCV JS or what? Because their build script only works on really ancient Emscripten, and really shame. Also, by default, OpenCV builds SMJS, so you have to specify for WASM explicitly, which is a bit strange. Next, please. Note that if you read OpenCV with JS documentation, they talk about calling OpenCV directly from JavaScript, which users probably mbind to bind all OpenCV functions and classes for JavaScript. That's absolutely not what we want. We don't want OpenCV code from JS. So we want to use OpenCV or functions in our C++ code. Luckily, it's not very difficult, but you don't need the OpenCV JS final build. What you need are point A files libraries which are generated during OpenCV JS build. They are C++ libraries, real C++ libraries, not JS files built with some script and headers from the build directory. Then you can import them in your C++ code in normal way, just like on desktop, C++ code, CMake project, or the be using C++. Even find package of CMake works fine if you specify the OpenCV build directory and then link OpenCV in your own C++ code. Once you understand how it should be done, it works fine. Then you create my code JS and use it from JS. And never use OpenCV JS created during OpenCV build. Next, please. The next question, I told you WASM is slow compared with native code. How slow? Let's take one particular test. Lucas Canada. Okay, maybe it's a bit extreme test because usually things are not that bad, but it's on the other hand, it's not unusual. On my laptop, native C++ for the same image size, same parameters, it will takes about 1 millisecond. WASM in Chrome, it takes about 24 milliseconds. WASM Firefox, it takes about 90 milliseconds. It's not a small difference, 20 times almost, or 90 times. Firefox is worse for some reason. Disclaimers. This is for the default OpenCV WASM build. If there are and all the version of Emscripten, if there are something exotic optimization, maybe I miss something. And all Emscripten version because of OpenCV and other C++ code can be bad. Lucas Canada is maybe an extreme example, but still it's not unusual that WASM, but still for WASM is expected that it's at least 10 times and maybe 20 more times slower than the native code. And don't believe advertisements that Emscripten is fast. I don't know why exactly Firefox is bad, but in this particular case, it was bad. Next slide, please. Next, now we're finished with Emscripten. Next topic are neural nets in the browser. There are basically two frameworks which people use. Other frameworks are exotic or deprecated. One is called TensorFlow JS from Google, and the other is called ONNX Runtime Web from Microsoft. They can use both WebGL, GPU. By the way, Evgen, you had a question about GPU. The answer is that web browsers can never use anything like CUDA anything like CUDA, cuDNN, OpenCL. I think do not exist in browser and probably never be. The only way browser can use GPU is WebGL. And as you will see in a few minutes, it's maybe better than CPU, but very inefficient compared to proper CUDA. So these frameworks, they can use web GPU via WebGL. The only way browser can use GPU currently. And they also had WASM and PureJS backends. Why does nobody use WebGL on the desktop? Why do people want CUDA? Because WebGL is very, very slow compared to CUDA if you are trying to do neural network. So WebGL is a JavaScript wrapper of OpenGL. It's fine if you want game engines. It's not very efficient for CUDA because you have to use shaders, things not made for neural networks in order to do neural networks. More on that later. Okay. But there is no CUDA in browser and probably will never be. WebGL has a pretty bad warm-up issues. It's unavoidable. First, inference takes a few seconds when the shaders are compiled. Follow inference are quick because the shaders are cached, but or leave the input tensor size does not change. If you have, I don't know, network with variable input and you change the input, then the shaders are compiled again. And again, the inference takes a few seconds, not milliseconds, not 10 of milliseconds, but few seconds. Think of that while the shaders of this framework are compiled. Next, please. I tried both these frameworks and quick facts about TensorFlow JS. First, it's not TensorFlow Lite, although I think TF Lite API is also available if really needed. TensorFlow JS is similar to Python TensorFlow plus Keras, as not identical. It has low-level tensor and high-level Keras-like layers. The worst thing is different from everything you have in Python, not directly compatible. It has its own format from neural networks like JSON and bin files. JSON network description and bin layer network weights. You can generally convert Keras or TensorFlow networks to TFJS, but it's not easy. For example, I had to hack JSON by hand, changing some settings in the JSON, otherwise it didn't work. TensorFlow JS has rich library of tensor operation, and you can resize, transpose, normalize, etc. You can also easily create a tensor from image or canvas, the HTML text, and the library automatically, for example, transforms RGBA into RGB. It can be used TensorFlow via script tag or npm and module and bundles. But example, send pre-trained solutions are bundler only from Google, are bundler only. I didn't try them. And for some reason, there is only blocking interface, no asynchronic. I forgot to say that TensorFlow JS is so big and have framework, it can even train neural networks. Although training in a browser is probably not a very good idea, I would say. And next, please. The second framework from Microsoft is called ONNX Runtime Web. It's very different. It's small, it's lightweight, it's from inference only, no training, no high-level operations. You have to create ONNX somehow from PyTorch or TensorFlow or whatever, and then you can run ONNX. What can I say? It would be good if not for major bug. There are major bugs in WebGL backends. For some networks, WebGL gave completely crazy wrong results. For simple networks like ResNet 18, it worked fine in all the version, but starting from version 1.09, everything is broken. And since then, there have been many versions. It's still not fixed. It seems that nobody really cares about this framework if the major bug in WebGL backend haven't been fixed. So the future doesn't look good. If nobody cares, the future doesn't look good. Basically only old versions can be used. It's a rather small and minimalistic framework, or ONNX format only, inference only. It has WebGL and WASM backend. It's good for PyTorch model because of ONNX, and it has absolutely no tensor operation, no normalization, conversion, anything. You have to do everything by hand, which basically includes either JS loop of a pixels, which is not as bad as in Python. JavaScript loops are pretty well optimized, or by some third-party JS library. So operation like resizing input tensors, converting to float 32, normalizing, and so on. Okay, next, please. I tried both frameworks and some comparison. How slow are neural nets in a browser? Disclaimer, I didn't do proper test. I didn't do control tests. These are very, very rough figures on my laptop, not proper testing regime. But what I did is a standard test case. What was that? ResNet 50, I think. And first I do PC, this PC Keras CPU, not in browser, about 90 milliseconds. PyTorch CPU 60-70 milliseconds, PyTorch Q the 5 milliseconds. That's what you expect. ONNX runtime interesting on PC. Interestingly, it's 15 milliseconds in CPU, much faster than PyTorch. So ONNX runtime is pretty good framework on desktop, especially if you want CPU inference, non-GPU. And now let's look at the browser. TensorFlow JS about WebGL 260. And also these are times they vary a lot, fluctuate a lot, but very roughly ONNX runtime gives 50 to 300 milliseconds. So ONNX runtime WASM gives about 1000 milliseconds. 1 second. So you can see WebGL supposedly uses GPU, but even with WebGL, the inference time of neural network is much longer than you can get on your computer on CPU if you are using desktop, like I don't know, just Python or something, not browser. So you see, browser makes things really, really slow, 10 times or more, and even WebGL doesn't make things really good. So that's what you can expect from browser. So in browser, anything larger than very small neural networks will likely take 1 second or more one inference. Understand this. Next slide, please. Now I'm almost finished with my lecture. Just a couple of more questions about other libraries which I didn't mention yet. What about WebXR, WebVR, WebAR? First, WebAR, such thing does not exist, at least as official name of any specification. WebVR is an old experimental technology which is now deprecated and I think probably removed from browsers. WebXR is a current experimental technology which is already experimental for many years. Can you use WebXR? To use WebXR, you need either VR device like Oculus and run in browser there, or PC plus VR device, some kind of glasses. That's the most typical scenario for virtual reality. Just on your computer, you cannot run virtual reality. It doesn't work. Or you can use phone with 3D glasses, also known as VR headset. So that's phone shows left and right image which are combined by the glasses. If you have such glasses, you can run on the phone. Without glasses, you will see two images, but nothing interesting. And finally, the thing which probably most interesting for a company phone with immersive AR. No VR, just immersive AR without 3D. It's possible, but only on phones with AR kit or AR core. My phone doesn't have AR core yet. Maybe I should buy a new phone, but many Android phones are still not equipped. Basically, that's it. Basically, what you can get with WebXR. It's interesting, but I didn't see. There are some demos. If you have the proper devices, and only if you have proper devices, there are many demos on the internet. Next, please. Other useful technologies for the web. 3GS is a popular three-dimensional graphics library, higher level than raw WebGL, but lower level than game engines. Babylon.js is another similar library. Unity engine. Nowadays, it's not some kind of fan port, but official Unity platform with USM and and WebGL. If you install Unity engine on your computer, it suggests you to do web builds very easily. A-Frame is also a RVR 3D library. I think it's not WebXR based, some older technology. FFmpeg.js is a script and port of FMP, a big and slow library which doesn't use native video audio browser support, but with FFmpeg you can really work with all the audio and video codecs with complete control. There are tons of other JS libraries which are with or without WASM. Next slide, please. And finally, the question to web or not to web, to use the front end or not use the front end. Just compare the typical PC console games and typical browser games, and you see the answer. Browser is like Raspberry Pi 1. It's platform 10 to 100 times slower than your computer. So my very next slide, please. So my very subjective opinion is that it's not very good platform for computer vision. Maybe you can get very lightweight computer vision, and but if you try to something heavy, then browser is simply not good enough. Don't believe the ads and fancy demos. Browser is much slower, 10 times or more than platform native code. And there are severe sandbox limitation, no access to files, etc. There is also resource misuse. Web turns your new PC or iPhone into Raspberry Pi 1. It's okay if you have something really super lightweight, maybe for PPG or dog breath or something, but for more heavyweight computer vision, you need all resources of your computer. You need GPU, you need CUDA, all CPU cores, and so on. And then you must absolutely not try to use browser for anything heavy. If you want to use serious computer vision, you need desktop or server, preferably with NVIDIA GPU, CUDA, etc., or Android iOS apps for mobile devices written in native languages like Kotlin or Swift. And also native Android apps for Oculus Quest and such, not web browser. Moore laws is not forever. Maybe you think that computers will get better, but for now, browser is 10 times or more slower than your computer. I think I basically finished with my lecture. Next